All right, so here's our objective today, starting chapter 4. To put everything in perspective a little bit with where we've been, we're kind of taking a step backwards and looking more at the big picture. We've worked so far with lines, quadratics, and polynomials, which are all specific types of functions. And now we're looking at kind of general properties of functions as a whole, not necessarily one particular kind. We'll talk about zeros, domain, range, and graphs, but just general properties of functions. A definition of a function is a great place to start. Okay, it's a correspondence or a rule. This is typically represented by the equation. For example, okay, if I were to have a linear function 4x plus 2, that's essentially a rule that assigns an element from my domain, which I call my x values, and it assigns it to an element in my range, which I represent with my y values. Now, the rule for a function is that it can only assign each x value to one y value. Okay? Lines are functions because if I were to evaluate x equals 3, I do 4 times 3, which is 12, plus 2, which is 14. Okay? So this rule essentially says that take your x value, multiply by 4, then add 2, boom, there's your y value. Okay? X equals 3 only gets paired to one element in the range, 14. Okay? That would be true for any other x value I put into the function, which is y. Lines are functions. This is an important piece right here. Remember that y equals f of x. Those two things could be used interchangeably. They mean the exact same thing. Okay? Domain and range can be a little bit tricky to find. Some patterns are often necessary. For example, I'll tell you right now, if you see a linear function, pretty good chance domain and range are all real numbers. Very, very few times, and usually it's within some type of application that we actually see that there's restrictions on the domain and range. Okay. Now here we see next three cases that all have domain restrictions. Okay, for example, square root of x. I don't want to get into imaginary numbers here. And negative numbers, when I take their square root, give me imaginary numbers for y values. And I'm not going to consider those a part of my domain. So my function, if I'm taking the square root of x, for my domain, I'm going to say that x needs to be greater than or equal to 0. Okay, I only want to be taking the square root of 0 or positive numbers. Okay, jump down to f of x equals 1 over x minus 7. Okay, what I want to watch out for here is dividing by 0. Okay, so I want to make sure my denominator can't be 0 because that would give me an answer that's undefined. And if my denominator is x minus 7, x equals 7 is the number for x that's going to give me some problems. Okay, so I'm going to specify in my domain x can't be 7, and again that's because it would make the denominator 0. All right. With p of x right over here, as far as the domain goes, again, yes, I see the square root of something. I don't want negative numbers, but here I'm subtracting 9 before I take the square root, so I have to factor that in. It's not just that I want x to be greater than or equal to 0. I want x to be greater than or equal to 9. Okay? Because if I make x equals 9, 9 minus 9 is 0, and that's as small an x value as I want to put in. Okay, so there it's x greater than or equal to 0. Now for the range, okay, if I put in 0 for x, and I take its square root, that would give me 0 for a y value, and then I add 2, which means because this graph is always increasing, y is going to have to be greater than or equal to 2. Okay. The range for this graph y can't be 0. This is another one that can be tricky to see. Doing domain and range from just an equation can be very tricky. A lot of times a graph is extremely helpful to identify domain and range. For this equation, this function, for it to equal 0 for the y value, this numerator would have to be 0. Okay? However, that's not going to work because this numerator is 1. It's constant. Okay? I can't change it. No matter what I put in for x, I can't make the value of that fraction 0, which is why 0 is not a y value that I can get. The range for p of x would have to be greater than or equal to 0 because, again, the smallest number I can put in for x would be 9. 9 minus 9 would be 0. Square root of 0 is 0. And from there, this graph is only going to increase. So I know that y equals 0 is the smallest y value I can get. Every other y value is going to be bigger. Let's take a look at domain and range from a graph, which usually is a little bit easier. Now to start with the zeros, okay, those are the same as what we've looked at with polynomials, so let's actually take a look at those first. This graph has a 0 at x equals 1 in part B. It has 1 at x equals 2 and 1 at x equals 4. Just know that the term 0 just isn't unique to polynomials. For any function that we say, hey, find the zeros, that's what we're talking about. Okay. So for domain, all right, all real numbers. All real numbers, okay? And the reason that's the case is I notice these arrows are going in both directions, which means that graph just extends forever, and any x value will give me an answer for my y value. Different story for the range. It looks like right here and right there, those are two lines, one at y equals -2, the other at about y equals 4, that this graph doesn't go past. Okay? What that means for my range, I'm going to state that y, actually it looks like it's approaching -2. Not crossing. And it hits this maximum point at y equals 4. So there for my range, I'd say that y has to be greater than -2 but less than or equal to 4 because it's in between those two horizontal lines. Same thing here with the domain, but now I'm looking vertically. And it looks like right here there's this vertical line at x equals 2, and the graph is never to the left of that line. Okay? All of that graph is to the right. So I would say there for my domain, x has got to be greater than or equal to 2. For the range, it looks like that graph doesn't go below that line y equals -6. Okay, continues to go above, looks like infinitely because there's an arrow on the end of that graph, but it doesn't go below -6. So I'd say the y value has got to be greater than or equal to -6. Okay. Big thing here is when you're looking at domain, think about these vertical lines and look left to right because that corresponds with the horizontal axis, which represents the x values. For the range, think vertical. Think up and down, okay? Because that corresponds to your y values. A couple quick things here. Two examples. One is a function, one's not. This one isn't because of these 2 points. Okay, remember the definition of a function states that each x value can get paired with exactly one y value. So we've got the x value of 2. 2 needs to make up its mind. 4 or 7. Okay, if this relation is to be considered a function, it can't go to both. It can only get paired with one. Okay, that's why that doesn't represent a function. If I look at the set of points on the right, I don't see that happen. Okay, 2 goes to 4, -1 goes to 6, 3 goes to 7, 4 goes to 1, 7 goes to 1. Oftentimes people think these last 2 points are a problem, but they're not. Okay? 4 is getting paired with 1. So is 7. What makes it a function is that 4 and 7 are each getting paired with one number. It just happens to be the same number. This case right here is different from this one. Okay, because again, this is an x value. This represents y values. Those are x values. And 1 is a y value. Okay? That's something to keep in mind. This is the one deal breaker right here, an x value going to 2 different y values. Along the exact same lines, if we wanted to tell if a graph is a function or not, just go to the vertical line test. Okay, this first one looks like a quadratic. I can draw a vertical line anywhere on that graph, and it touches the graph at exactly 1 point because it's a function. Okay? The circle is not. I draw a line right here, and there, and there. Those 2 points are touching that graph more than once. That's not a function. Okay? So anytime you want to tell if a graph is a function, you can always refer to the vertical line test. You would say, for this first one, you know, if I had to justify it, I could say it passes the vertical line test, which I could just refer to as VLT. This circle right here fails the vertical line test, which is why it's not a function. Graphing to do here to finish, okay? Kind of an interesting little graph we have going. We haven't seen these before, but we can have a graph like this where it depends on the domain as to what graph we're going to use. This says g of x is x minus 1 if I'm talking about negative x values. If the x value is between 0 and 3, well then I'm going to follow a quadratic. If the x value is greater than 3, then it's the constant function at y equals 0. Okay, let me zoom into my graph here. It said graph the line y equals x minus 1, okay, for any x values that were less than 0. So there's that y-intercept, plotting a slope of 1. Okay, now as I graph these points and connect them, I stop right there because that gets me to x equals 0. And this graph said, graph the line y equals x minus 1 for x values less than 0. So I'd stop right at that point. Now I'm going to jump over to 3. It said if x is bigger than 3, do a constant function, okay, at y equals 0. All right, so I've got those first 2 on there. Now I've got to do this goofy little one that's in between. It says for 0 to 3, for those x values, graph this quadratic. Well, like any quadratic, I want some key points. It's factorable. Split it up into 2 factors of x minus 3 and x plus 1. Okay, using negative b over 2a, the axis of symmetry is 1, or I could just say halfway in between the x-intercepts. That should be f of 1, which will be negative 4, so that's the vertex right there. And the y-intercept is negative 3, so this should be enough to finish off this graph. Okay? So right here, there was an x-intercept. Vertex was down here at 1, negative 4. Y-intercept was right there. Notice I'm not going to plot the other x-intercept because it takes me over to negative 1, which is not in the domain. This is just supposed to be graphed from 0 to 3. Can I mark my vertex a little bit better right there? Kind of an interesting little graph. Okay, same graphing techniques, but it just depends on the domain as far as which graph I used. All right, that's all for 4.1. Be sure to ask more questions in class if you had any issues with any of the material.